so.
Yeah.
Okay, no, then, yeah, let's continue with the lectures for Subhroneel.
Thank you, Sam. Okay, so let's start. Lecture. So let me start by sort of maybe apologizing a bit because I realized that in sort of going back and forth between the two conventions which Ashok used and the one that I'm used to, which Lambert used, I realized that not all the factors were converted exactly correctly. So some of the factors in the last lectures are slightly off. They're mostly harmless because you can just, it's just a factors of 2 and 1/8 and stuff like that. But I decided in fact, what was worse is that the action that I wrote down was not entirely either of their conventions. So, which in my mind is the worst thing. So what I will do today is that I would from now on stick entirely to the convention that I am used to because we are discussing explicit calculations and papers by me and collaborators and stuff like that. So in our Lambert's convention, we would write the action.
And this is the same as Lambert's?
Sorry?
That's the same as Lambert's?
That's the same as Lambert's. Yeah. So I would write the action like this. Nothing has changed in the P kinetic term. There is a change in the Q term, which is essentially replacing the Q that I wrote back time last time by -2 of Q, right? Which is a harmless change. And there is also a change in M, I think by a factor of 1/8 or 1/4, something like that. Okay. And with this change, it works. And everything I said last time, the construction and everything that just holds true. There is no problem with that. So because there is this slight confusion, let's just quickly do one computation, and then in fact we can do a new computation so that people are not bored. And which is something that we would need today, is that we would want to now turn on sources for a self-dual field strength, which is now coupled to some non-trivial metric to this map N. So the way to turn on the sources is that the source I'm calling K, just like I think second lecture. And we already saw this term when we discussed the example of the sources in flat background, right? Now there's a new term that I wrote down because the source can also depend on the count. It can couple to the self-dual field strength Q through some sort of information in geometry. And I will just now explain that why this is the sort of correct way to introduce the sources, because we know how the equations of motion should look like in presence of sources, and this will give us the correct equations of motion. Okay, so let's just quickly go through the motion. If you vary with respect to P and set it equal to 0, this gives you from here as V star P. From here you get twice D of Q, and you set this equals to 0. And what we would do is that we would rewrite this thing as D of half 1 plus star dP plus Q equals to 0.
Oh, and the two M's are the same.
Sorry?
The two M's.
The two M's are same. The two M's are same. There's no difference.
It's just a map, right? To take it from something to completely anti-simple version of that. So M is just a map of.
M is just a, so to remind you, M was a linear map, which mapped, so if you had a self-dual eta form, M mapped it to an anti-self-dual eta form.
So K is already anti-circular, right?
No, K is in general it's a general form.
Okay,
Okay, so yeah, you're probably thinking that
yeah,
it's basically taking the self-dual part of the K and mapping it to the anti-self-dual, some sort of anti-self-dual thing, which then contributes. And here only the anti-self-dual part of K contributes, right?
okay.
But we would need the full K.
Okay, I see, okay, thank you.
So in the flat space,
So, sorry, so
Yeah.
M of K includes, anti-self-dual mean, like, so you had a generalized version of M, which
Right.
takes anything to anti-self-dual.
right? So
So is it that or?
it's that. It's that.
So, but in that case, M of K will take, anti-self-dualized to be the same,
Mhm.
and the self-dualized to be anti-self.
Anti-self-dual part will get mapped to 0.
Oh, okay,
So K I can write it as some sort of K plus K minus, right? And then M of K is effectively M of K plus.
right, okay,
Because M of K minus is by definition 0.
okay.
So if you want, you can rewrite all of this in terms of K plus K minuses, but that will just make it more cumbersome.
Okay.
And eventually we want to use this thing to make connection, concrete connection to type 2 supergravity, where we would see that this K itself is a natural object to think of,
Okay,
without further decomposing it into K plus K minus all the time, which you can always do.
thank you.
And why do we call it ether form? You just mean ether is just a form, right?
Yeah, because
I'm not sure about
yeah, so
Okay, so self-dual with respect to the ether.
yeah, so last time we discussed that this star is always going to be star with respect to eta.
So I probably would call that ether self-dual form.
Yeah, that's also a point. So we are on a curved manifold with metric G, but this action uses certain things which sort of behaves like a form if the metric was bigger. But as we saw last time, that P and Q, neither of them transform like a differential form on the physical manifold. But they have properties with respect to etas, so that's why it's important to distinguish between them, right? Okay, so here the only thing I did is that you get rid of this minus sign, you bring the 2 here, half, and you add a trivially 0 term, which is b squared p equals to 0. Right? That's the only thing I have done. But then what this allows us is it allows us to identify what is the additional field which decouples. Right? So in this notation, this would be my HS. So I would write this as b of HS equals to 0, where h of s is half of 1 plus star b plus 3.
So why didn't you subtract it, the one instead of adding?
Because I want this to be self-dual.
To get the same?
Because remember in the quantum theory, we saw that the quantum theory, or even in the interaction level, is a quantum theory of an additional self-dual field with a wrong kinetic term. But then there was an interacting self-dual thing. So we know that the additional thing has to be a self-dual object. So this is the natural way to make it self-dual.
So there's no information to get from taking the other projection?
If you can, so as I said, that the correct way of seeing that what is really the additional degree of freedom which gets propagated out or projected out is by looking at the Hamiltonian analysis. It's just that once we have done the Hamiltonian analysis and we have figured out, it's always very easy to look at the equation of motion and identify that what is the self-dual combination. So then this is the only way you can make it self-dual.
So 3 lectures ago, so you say subscript S was because of scalar, but is the real was self-dual?
No, it's because this subscript H is because of singlet, like it's scalar or singlet. Yeah.
You stay with it.
But yeah, I differently speak with that. Yeah, but it's also true. It has always been true that HS is by definition star of HS. Right? Because Q is by definition star of Q, and this, of course, it's designed with that. So previously in our last lectures, we didn't have this half here, and we had a minus sign, which is perfectly consistent with what I said, that we replace q by minus 2q, and then this becomes plus, and we can bring the 2 out overall. And it's just saying that whether h's or 2h's is your field, but that's like a trivial.
So, what it tells you is that that combination is closed.
Mm-hmm.
And self-dual.
And so with respect to eta.
Right. Now, if you did the other thing, you subtracted, so then you would have something which is also closed.
Mm-hmm.
But then you would have a subdual part and an anti-subdual part.
Right.
Is there any non-trivial way that these parts could cancel when you take D on it?
No, I would say that simply because h's, if you have something which is so given this, right, I can always change h's to h's plus d of something, and that doesn't change the equation motion. So the other part is basically like that. You're basically adding some alpha dt. It's basically just using that sort of gauging variance, if you like. Which of course the P sector has, because it always enters through dp, so it's always going to have a sort of usual gauging variance, Abelian gauging variance that you would expect. So you always have that freedom. But the point is that, as I say, that in the Hamiltonian analysis, there we don't have any luxury. Once we have figured out the Hamiltonians, we see really that the Hamiltonian splits nicely into 2 Hamiltonians. And we know that the additional degree of freedom is that of a cell. So you choose this such a way that you retain only the cell glories. But of course, I mean, I always have this freedom. I can always shift it by d or something without changing the dynamics of the additional cell. Okay. Okay. Okay, good. So this was the additional non-physical sector. Then there was the other one, other equation of motion where we vary with respect to q, and you set this equal to 0. And this gives you from this part. Remember that because q is self-dual, only the anti-self-dual part of this would contribute. And once again, this is self-dual, so only the anti-self-dual part of this will contribute. Plus minus plus. So this portion we can simplify using this definition, right? So we can, so okay, first thing is that you take another d of this whole thing, which is also 0. It helps you to get rid of the first dB. Then d star dB, you can eliminate in favor of dq. So that's the simplification that I'm going to do on the first term. D of dP vanishes. D star dP, I'm going to use this equation and express it in terms of dq. So this gives you minus 4 dq. The other terms I don't have to touch. They can be as it is. This portion, let me combine them a bit. Let me write them as okay, first let me just simplify this a bit. So let's define k plus minus as here. So remember k plus minus is half 1 plus minus k. And in terms of this, you could write d of a minus star k as twice d of a minus. Is this obvious?
Okay, I'm still
Yeah.
trying to figure out what you did with dp. Right? So you have dp minus star dp,
Mhm.
and that's replaced by dq. Are they?
So I took a,
Oh,
so,
there's a d outside.
yeah, I took a whole D of this whole thing.
Yeah. Okay.
Yeah.
No, okay. Yeah. Sorry.
No, yeah, it's fine. So is this clear? So K minus star K will be twice K minus, I took a D on both sides, that's it.
Yeah, that's more or less the definition.
Yeah, that is just follows from the definition of K minus. So this one, I can just replace by, so it's minus 4 dq plus 4 dq plus 4 dk, then plus 4 k minus equals to 0. And nicely, all of them has a factor of 4, which means we can just forget about them. Now we can rewrite this as minus q plus k minus plus m. Now remember, this m is a linear map. So m of q plus m of k is same as m of q plus k. Right? So this is equals to 0. And now what we want to do is that we want to re-express this k minus. So remember, k equals to k plus k minus, or we can express k minus as k minus k plus. So this becomes d of minus q plus k minus k plus m of q plus k equals to 0, or just add dk on one side, and then the rest of it I took on the other side, so which becomes opposite side. Okay, and as Masu was asking in the beginning, that because am is acting on q plus k, and it's only going to basically act on the self-dual parts of this, guys. So you might as well just replace this by q plus k plus. Q, of course, is by definition self-dual. There is no reason to add q plus. It's just q. And now, if you remember, our definition of n was that if you have a self-dual thing, then this particular linear combination is going to be self-dual with respect to the physical metric. That was our definition. So we said that if you have q to be beta self-dual, then q minus m small q, by definition, let's call it some, I think I call it small m of q. And this small m of q is by definition self-dual with respect to the physical metric. So this capital M was constructed in such a way that this property was satisfied by construction. So now, in presence of the sources, this then is our physical self-dual field strength, which is self-dual with respect to the curve metric. So this is what now we would like to identify as H of. So we will write this equation as D of H of G, with the same as D of star G H of G equals to dt, which is how you would expect the equation should look like if you have derived from say pseudo in presence of sources. And I also told you what is the interpretation of K in terms of the current. That if you have a constant current D star J equals to 0, then you can always express star of J as D of something. So this D of some K is basically that. So it's basically replication of whatever we did last time, but now in presence of sources. And why are we turning on sources? Simply because supergravity has them. You have the Raman 5 form flux, which is sourced by the other Raman fluxes and the Calderon and so on. So if you want to make connection to the type 2 supergravity, you have to know how to handle this with sources. So this is just a generalization, and it also helps us in sort of fixing the notation and seeing that how in this new notation everything works. Okay. And the definition of M, capital M, this map construction, everything I said last time, it's exactly the same as it is. Nothing has changed. Okay. So now, if you were just interested in a cell-to-cell field strength in some power manifold in presence of some sources, then this is where you would stop. You have the right equation of motion, and then you would try to solve these equations of motions or do some whatever you want to do with it. But we want to identify this setup, specifically in 10B, with the type 2 supergravity pseudo action formalism, which we see in the textbooks. So for that purposes, it would be nice if to this action S, we had two following terms. Both of these terms that I've added is something that purely depend on the sources, K. So it has no bearing on this equation of motion. Because you either vary with respect to P or you vary with respect to Q, which are your dynamical fields, and both of those are completely insensitive to the two terms that I've added. And at this point, it seems like a completely ad hoc thing that they just have added. But it's going to make sense that why you need these two terms in next 15 minutes or so. Because short answer is that these are the terms that has to be there if you want to make connection to the textbook formalism of the type 2 supergravity. Okay. But for now, just think of it. I mean, all of us agree, right, that if you replace this action by this action plus these two additional terms, none of the analysis that has been presented in this section has any effect whatsoever. I'm just adding two terms which are completely harmless. Okay. Almost. Seems to be something around the page. So please tell me how low I can get.
We can check there.
That's okay. Yeah, I think this is fine. And you can see it's.
That's perfect.
Okay, one nice thing, once we add those two terms, is that you can rewrite this action with those two terms in a slightly nicer way. And there it is. Or maybe for this thing. So the only thing that has been done is that you can just simply expand this product out. Remember, A is a linear map, so M of Q plus K plus is M of Q plus M of K plus. Expand this product out, do some cancellations, and you can see that this is precisely what you will get. And this one is basically the same as the last step, just re-expressed in terms of K minus and K plus instead of K and star, given the definitions that you have. So the half goes away because K is like K plus plus K minus and K plus minus K minus. So the two cross terms, both are the same, they add up, and that kills out the half. Okay. Now, it might not look very nice to you right now, but what is particularly nice about this is that the M appears only in one term. The gravitational coupling appears only in the one term. Right. So that's a good thing. And this action, let's propose some transformations for them. So let's say lambda is some that. And let's propose the transformation is that delta lambda p is lambda, delta lambda of q is minus half the star d lambda, and the sources they are from this. Let's just propose this transformation. It's not completely ad hoc. If you remember from your textbook, then you should remember that in supergravity, these sources have the thing that it transforms like a transformer star. This is precisely that kind of a transformation. For the P and Q, of course, it has to be something quite new because P and Q variables are not something you see in your textbook formulation of supergravity. Under this transformation, it's a very straightforward calculation, and you can check that delta lambda of S is going to be this. So just take this set of transformations, plug it in. There is a huge amount of cancellations that's going to happen. Right? And then one quick thing that you can check is that the combination HS, this from this definition is going to be invariant. Because look at HS, it's basically half 1 plus star dp. So when you first heat it with respect to the delta lambda, it's going to give you half 1 plus star d lambda, which is precisely going to be cancelled from the delta lambda. And you can also check that the HG is also gauge invariant. The other thing. And among all the other terms that we have written now, the only thing that survives is this. And now what we would like to say is that, okay, we want to expand the set of gauge transformations, or rather restrict the set of gauge transformations from this to only those lambdas for which this is identically zero. So we put one further condition that lambda is such that given a source A, this thing will identically vanishes. You can prove that both of the field strengths, the physical and the physical, are the gauge invariant quantity.
But that was before you imposed this last condition, right? For at least for the first one.
These two are kind of insensitive to this condition,
right?
But the total action,
right,
that would require you to, of course, impose this. So if you want these transformations to be a gauge transformation, then you have to. But this is actually a good thing, in a sense that if you did not have that, it would have implied that P is pure gauge. Because look at these gauge transformations, it's basically just simply saying that I can set P or shift P by any arbitrary P form. So I could just as well have set P to 0. And which would have made that, everything involving P and Q in the first two terms, they just drop off. And that's a very bad thing. So this is the thing that restricts P from becoming pure gauge. Okay. So this is a set of gauge symmetry that this action has. There is another set of gauge symmetry it has, which is the trivial one, where you, let me call it lambda 1, delta lambda P is some P of lambda 1. Now lambda 1 is a 2n minus 1. And of course, everything else is unchanged under this. This is obvious, right? Because you have everything comes with a dp. And if you change p by d of lambda 1, dp doesn't change. So that's clearly a symmetry of the action. Right. This one is not going to be that interesting because it only is a gauge transformation of unphysical set. It only cares about what is happening because P only enters the unphysical set. It doesn't enter in each statement. But this is interesting. And why is this the interesting one and why do we even talk about it? Is that now let us try to make a connection with the pseudo action. So far, this is all in some general 4n plus 2 dimensions. I'm soon going to specialize only in 10D and the active supergravity. But to the extent things can be general, let's just keep them general. So consider a pseudo action. I don't know what it is. So let's call it as here. And it's defined. So C is some unit form, which is typically your gauge potential, and K is a source, just in the sense case. I'm deliberately using K because you will see that it turns out to be the same K. Everyone is familiar with this sort of action, right? This is typical round kinetic term that you would have in any supergravity, not just activity. So you have the DC, then you have some sort of shift involving the Chern-Simons terms. Then there's a wedge product with respect to the physical metric, the actual physical metric. And then there is a sort of source term that you have. So given any round potential, there is always some K which you can, just that portion of the supergravity action, you can cast it like this. And of course, we are going to see explicit example when we discuss the technique. And how does this work? Okay, first you vary with respect to C, and then equal to set equal to 0. And this gives you the equation E of star T C plus K equals dk. And on this equation of motion, you now by hand demand that this combination C plus K, let's call it some F hat, something which is self-dual with respect to the physical metric. And this is something that you purely demand by hand. Up to this, it's standard Euler-Lagrange equation. But then if you demand it by hand, then you can recast this equation as D of F hat equals to D of star G F hat equals D of. So this is how you would do type 2 supergravity in the textbook. Any textbook that you pick up, the single action formulation. It's just that now it has been sort of recast into a more general 4n+2, but that's how it works. If you have a self-dual system in an arbitrary curve background in presence of sources, this is how the equations of motion is derived. Up till this, you can do it systematically, but then you have to by hand demand that this is self-dual, and then you can get it. And now compare this with this. Now it's very clear that how to make connection to the single action formulation. You have to identify this HG, which is a self-dual with respect to the physical metric form with this F hat. So on shell, we identify F hat with HG. That's how you make the connection. that gives you the same equations of motion. That maps this equation of motion to this equation of motion and vice versa. And you see, we didn't have to do anything to the K. The K can be the same source. So the K that would naturally appear in the pseudo action is the same K that appears in sense action, which is a good thing. Because K would turn out to, in supergravity, which is typically the other round sector of the color things. And for them, we never had a problem with writing down action. So we don't want to modify them. Right? But this is not enough. This action is also something that has a gate symmetry. So let me maybe use the color. So gate potential changes like this, and force changes exactly like that as it was before. I'm deliberately using the same H parameter lambda. Under this, you can once again show very straightforwardly that this is. So once again, if you demand this to be 0, then your pseudo action is gated. This is once again a very textbook thing. And now you see why we needed to, so at least partially you see that why we needed to introduce those two terms. Because if you want to make connection to this pseudo action, it's not enough that you make connection to the same equations of motion. You also have to make connection with the gauge transformations that those systems have. So because this pseudo action formalism has this additional gauge transformation property, you need to make sure that your whatever alternate formulation you're giving also has that same gauge transformation property. And you should always remember that you can always make connection to the pseudo action only on shell. Because off shell, this is a completely different theory. It's describing a theory of a general 2n+1 field strength. No circular property or anything. So it's only on the space of solutions that you can meaningfully talk about going from this to that. But the advantage this has is that now we have actually a well-defined action from which we have derived this thing without imposing any by-hand constraints or whatever. That's the superiority, which means that you can actually use this to go beyond the classical computations, whereas this is only something you can do to find classical equations of motion and solutions. Okay. Okay. So this is the point where I stopped talking about specifically some sort of 4n+2 dimensional thing, and now we'll just focus on 10-dimensional dynamics projection. Right, so we can be a bit more explicit what K is and what C is and so on and so forth. And what we are going to do now is that we are going to show that you can use Sen's formulation to write down a covariant action for active programmability. And that on shell gives you exactly what you would expect. Because equivalent sum of active programmability is it's not controversial. Everybody knows that. Because motions have been unambiguously known for 40 years. Okay, so any question at this point? Okay, if not, let's. So So what we want to do is that let's first remind ourselves a little bit about the superaction. What's the status? So you have some S delta, and you can write it as sum of two terms, S1 plus S2. And what do I mean by S1 plus S2? S1 is all the terms that involves C4, which is the Raman potential. So open the textbook, look at all the terms in acute supergravity. Anything which has C4 involved in it, just club them under some label for S1, and everything else we call S2. Okay. So now, how does S1 look like? And okay, I mean, it's quite clear that the problematic sector is S1, which is why we are decomposing it into like this. S2 has no problem whatsoever. S2 is perfectly fine, well defined, no y constants, whatever it is. S1 is only the problematic piece. So how does S1 look like? S1 looks precisely like that, but now we can sort of generalize it a bit. And where we say find that the twisted Wilson. And this key is precisely what we would get. So in presence of the Calderon and the Raman fluxes, the cell dual guy is basically this twisted combination, right? In terms of which you have to write down the traditional candidate form. And this immediately allows us to identify that what is the K. The K is something that I have written it as B2 wedge F3. And F3 is precisely the standard phase strength of the Raman form potential. Yeah. Now I want to point out one thing about the Chern-Simons-like term that you have in supergravity. Is that remember way back in the first class I discussed that Ashoke's formalism is something that tells you that for all Raman sector, we have to do something similar. For the cell-dual field strength, we didn't have any other alternative. But if you really derive a low energy effective action starting from the full string theory, all the Raman fields actually should enter through only their field strength, not their potential. Okay. Now you might wonder that how is this going to happen or get affected in the Chern-Simons terms. The good news is that the Chern-Simons terms always comes in the form where there is one Calderon and two Raman potentials or Raman field strengths. So which we can always integrate by parts and always write this thing as B2 wedge F3 wedge F5. This is precisely that time. BC4 is the F5, untwisted. Sometimes in textbooks you will find that this thing is maybe written as C2, and then this is changed to the field strength H3. Of course, with up to a minus sign and etc. But then what I'm saying is that if we really derive it starting from a space-time action of string theory, you would actually never see this form. So naturally, the form that would come is always going to be the Calderon potential times the Raman field strengths. That's what I'm saying. And this wouldn't have been possible if there was not a potential sitting there, which is the Calderon potential. And you might wonder that, okay, what's happening with the Calderon thing? Why is that not appearing in field strength? Simply because if you construct the vertex operator for the Calderon, It's the potential that which changes. Unlike the Raman sector, where it's directly the field strength which changes. But for the chiral Raman, it's really the B mu which enters the vortex operator. So the string theory or specific action of string theory is sensitive to the chiral Raman potential, but not the Raman potentials. Okay, so that's a good thing, which means that we can always rewrite this thing such that no Raman potential explicitly appears. It's always the Raman fluxes. Yeah. Okay. So this is our K. It's B2 with F3, and this is the standard textbook action for the S1, right? Or in fact, let me. There is no reason to only focus on the bosonic sector. If you write down the full supersymmetric completions, then Ka would be, of course, it will have this part, but then it would also have contributions coming from the superpartners, which would be some fermionic bilinears and combinations of them, and so on and so forth. So in general, K is some sort of big object which you can identify. The bosonic part is easy to read off from the Chern-Simons diagram, but then in general, it has some other things. Okay. So this is really just a textbook story so far. Now, what we want to do, or what Ashoke does, is that we want to just replace this side. So, since action for type 2B is basically this, where S, by this S, I mean what is written up there on the very top. But now think of it in 10 dimensions with K to be described. P and Q are new fields, right? How this P and Q were connected to the physical field, we have almost already figured out. I just need to recast it in the standard language. And K is precisely this combination that we have.
But before we used equations of motion for PE as a fundamental thing. Now it's actually a combination of two things. Does it change anything from the
No,
to work?
I mean, I'm still going to think of those actions as a function of P, Q. That's it.
Right, but if I'm thinking of it as a Lagrangian, including a bunch of fields, my variation would not be okay, but like B or C2 or
that's a different point. I'm coming to it. So only thing that I've done here is that I've replaced the C4 dependence by dependence on two new fields, P and Q. Now, the other part is what you were trying to precisely point out, is that so far in that general analysis that we are discussing so far, A was acting like a source. But in full type 2 supergravity, A is not just a source, right? Of course, it's sourcing the Raman 5 flux, but they have their own dynamics. S2 has terms which is going to give dynamics to B2 and F3 and so on. So I need to sort of see that whether this whole thing sort of maintains that structure as well, which is something that I'm going to show you, right? But yeah, you're right that A is not just acting like a source in itself, it's also becoming dynamical, which answers the second part, that why we needed to add those terms. Because if we had not added those terms, the equations of motions that would be K equations of motion, the things that appear in K equations of motion, those won't match. So that's the reason. Okay. So right now, this is just a proposal, right? To check that this is really the correct. So if somebody comes and tells me that I have given you a action for type 2 supergravity, the first thing I have to check is that whether it reproduces the type 2 supergravity equations of motion. Those equations of motions are known unambiguously, and I should be able to reproduce them. Right? So we have to check that. Now, For the Raman 5 form flux center, it's relatively easy. We just need to identify this 85 hat with the HG that you would construct from the sense action. And with that, this general thing that we have proven there, it guarantees that both of the equations of motions are exactly the same. Right. So the physical on-shell Raman 5 form flux, which is self-dual with respect to the background physical metric, is precisely the combination HG that you would construct from sense action. So with this, the RR 5 flux equation of motion is satisfied on both sides. Now, there is a second thing, is that we have also proven that they have the same gauge symmetry. Now I can that general gauge symmetry I can write down even more precisely, like in terms of how P2 transforms, how C2 transforms, and so on and so forth. And we have
Maybe the right word is to say you lift your Fs to H. Because Fs only of this makes sense in the server action.
yeah, I mean I would say that
Because you make the identification only on shell.
exactly.
So maybe you should write it. It's more like you're lifting it by actually a new object.
Yeah, I'm just simply saying that on shell I identify F5 with H. Right. That's a thing. If you do that, then the F5 equation of motion is the generalized Maxwell kind of equation of motion is exactly the same that you would get from sense action, which you can derive as an Euler-Lagrange equation. And from here, you cannot derive it as an Euler-Lagrange equation. It's an Euler-Lagrange equation plus something that you demand by hand. Then the two equations of motions are exactly this. Then we also have shown that the gauge symmetry is the same with same gauge parameter. There is another place where F5, in another equation of motion where F5 plays a role, which is the Einstein's field equation. Right? There is one equation of motion for F5 where you're looking at what is the dynamics of F5. That's the generalized Maxwell's kind of equation. But then, of course, there is a Einstein field equation, right? When you value the whole thing with respect to the metric. And there is a contribution to the stress energy tensor from the F5. Raman 5 form flux has some energy and momentum, so it's going to contribute to the energy momentum tensor, right? This will also match simply because the stress energy tensor is going to. So there is a contribution to the stress energy tensor when you hit the variation with respect to S2. So when you vary the S2 with respect to the metric, that is same for both of them because it's the same S2. And last time, I didn't actually get the time to prove it, but I at least quoted you the result that the stress tensor that you get from the pseudo action with this on-shell, this by hand condition of self-duality is precisely the stress tensor that you get from variation of sense action. So they both give you the same stress tensor on-shell. So Einstein's field equation is also not changed. This is because P mu from pseudo action with by hand demanding F5 to be dark F5 is same as the P mu that you would derive from sense action. And of course, there is another contribution to the stress tensor that comes from S2, which is exactly the same for both of them, because it's the same S2. The only non-trivial check that we need to do now, which is not covered by whatever we have discussed so far, is precisely the thing that Ricardo was pointing out, that K is no longer just a classical source. it is a source for the Raman fractal class, but it is also a dynamical field or composite of dynamical fields by its own right, because S2 will have terms which gives dynamics and it comes to this things that appear in K. So we need to show. So let's call every other field that is there in this action except for the Raman fractal class, every other field in the that will be spectrum. Let's call them some sort of capital phi. Just collectively. Now, there are going to be two types of capital phi. One class, it does not appear in S1 at all. So there are some fields which do not appear at all, right? There are some supergravity fields which are not making an appearance in S1 at all. So all of their kinetic and interaction pieces all of them are sitting on S2. For those kind of fields, it's very obvious that the equations for motions have not changed because S2 is the same for all of them. So the equations for motions for those guys would be delta phi S2 equals to 0. And this is same for both reaction and sense. So these are not the problematic fields that we need to worry about. There is another thing. So now we have to worry about things which do appear in S2. Sorry, S1. And there are essentially two kinds. One which appears in S1 in K. So it's sitting inside the definition of K. And one is basically the metric. Right? Because there's a G sitting here. Or if you want to think of Ashoke action, there's an M sitting there. But when you vary with respect to metric, that is precisely the stress tensor thing. So this is already covered in this 3 point. So don't worry about the metric. So these are the only kind of fields for which we need to establish the equations of motion are not changed. So these are the fields which appear in the definition of case. Okay. Oh. I would prefer not to erase this section, so it's points. Okay, some of the yellow is not getting erased pretty well. Okay, so what we need to prove is delta phi of S tilde. And now by phi, I really mean this category, things that appear in K. This is same as S2B in Ashoke's formalism. Right. So there are two contributions. And what we really need to prove is essentially this. Because both of them has a contribution which is delta phi S2 which is same on both sides. So those parts will of course always empty. The only non-trivial check that we need to do is that when you take the S1 and vary with respect to these extra fields, and because it's an on-shell condition, you have to remember that it's okay for you to now by hand impose a self-validity condition. And on the other hand, in Ashoke's case, there is nothing to impose by hand. You just simply vary it with respect to the field and you get what you get. And they better match. If this is to be a correct action for the database. Yeah. And in evaluating this variation, this is precisely a variation which is only going to hit the K. It's not going to hit in the pseudo action, it's not going to hit the C4's elusive. And on the sense action, it's not going to hit the P and the Q and the M. It's only something that hits the K. And that would be enough. You don't need to really figure out that what exactly is the variation of K. This information would be enough to establish this. Otherwise, it would be like if you check case by case, it would be a tedious job. So is it clear what we're trying to prove here? Okay. Okay. So let's do one by one. Let's start with the simplest thing. Let's start with the LHS, which is the pseudo action first. So this one is up there, and it's a straightforward thing that vary with respect to this. With this. Right. In the first type, F5, so it's first and foremost, it's completely symmetric. So it's okay to just hit any of the one variation and you get rid of the factor of half. And then when whichever F5 you make it hit, it's basically going to give you delta by K, because delta by BC4 is by definition 0. So that's this. And then the other one just comes along for the line. Right? And then the last one is very quickly. I just switch the order, so there is a minus sign. These are all odd forms. So whenever you switch order, you pick up a sign. Yeah. And so far, I have just done this part. I have not imposed self-validity by hand yet. I just simply taken a variation. That's it. Now, if I impose the self-validity condition like this one, then I can just simply write this thing as and BC4, we can write it as F5 hat minus P. Just to re-express everything in terms of the field strength, user field strength, and the source itself. This gives us so without telling me what is exactly phi, I can't simplify any more than that. If you tell me, okay, phi is V2, then I know how to simplify this and so on and so forth. But this would prove sufficient. Okay. So let's call this equation some name because this is what we are after. So LHS has been simplified to this. Now RHS also needs to be simplified to this. Is it clear? In this case, I just simply replace star G by DC4 plus K, which is nothing but F5 there. And then dash DC4, I just go by F5.
The variation of K could produce D's on the variation, which means that you're doing it in the action, you drop the integration, of course. So it's in the action, so then you should, right? So then you should partially integrate. So you could get terms which is D on what you have
This can simplify even more if you tell me what is phi and etc. But I'm saying that inside the integral, this is definitely true. Whatever k is or whatever phi is, this is definitely true. It's just a variation. If you want to think about it, this is a variation which holds everything else constant except for k. And that is precisely the variation that we are going to do, the class of variations that we are going to do if we want to look at the equations of motions for any of the fields which make an appearance inside it. And of course, if you give me a specific field, then and I know the expression of k, then I can simplify even further. But this stage of result is definitely universal for anything that appears in it. And this is sufficient for our purposes. This form.
Well, I mean, inferring that this is now what's in the bracket is the equation of motion is not.
We are not going to sort of say that this is the equation of motion, because if we can prove this, that's enough. Setting this equals to 0, automatically we imply that equals to 0. So we are just showing this equality at the level of variation.
Wait, no,
itself.
no. So you're proving they are equal, or you're proving that both are equal to 0?
I'm proving they're equal, which is a more stronger result than proving them to be equal to 0.
Yeah, but I thought you said no. You're proving this equals to 0 is proving that equals to 0.
No, I said that if you can prove this, then it automatically follows that if you set this equals to 0, then you have to set this equals to plus 1. But what we are proving is this. This is precisely what we are proving.
Which don't make sense because you have subtracted the H2 part of both sides.
Exactly.
So
I cannot say this equal to 0 on this one.
why? You want to see the difference in that.
Exactly. This minus this is 0. That's the only statement I can make concrete. That's it.
Okay.
So this is for the pseudo action. So let me just sit out. Now, maybe this one. Sorry. The RHS. So, okay. This delta phi, as I said, is something that only hits the k. So it's the only relevant part of the full action is basically something that comes from this, and this. The first two terms are unimportant for this particular analysis. Okay. And in fact, even if you expand this full product out, there is a term which is q wedge and q. That is also not going to contribute. Right. So if you expand this product out, you get one term which is q wedge and q. That is not important. You get a term which is k plus wedge m of q. And then you get a term which is q wedge m of k plus. Now remember I told you that m has the symmetry property. That if there are two cell-dual, eta cell-dual forms, some q1 and q2, q1 wedge and q2 is same as q2 wedge and q1. So those two terms are exactly the same. So that one of the terms are going to be that. And then of course there's a term which is k plus wedge m k plus. That is of course going to contribute. And then there's going to be contribution from this and this. Okay. So the relevant part of the action on which this hits, let me call it say is relevant, is twice k wedge and q plus k wedge and k wedge q. And for the time being, I'm just replacing everything by k's here, so we don't have to worry about variation of k plus and k minus separately. It just makes our life simpler. So it makes sense to go back to this k with start k form that we had earlier. It was this. Okay. So this is not a full thing, but this is the relevant part. When I hit it with the delta phi, this is the only thing that is going to contribute. So that's why I just said relevant. Okay, and also to save space, we don't need to write in terms which are not going to play a role. So now if I vary with respect to this, so delta phi s is basically going to be delta phi s relevant. So you're going to have
One question.
Yes.
I've asked before.
Yeah.
QH K, you can just write it as QH K minus, right?
Yeah,
They are both the same.
they're both the same. The only reason I'm not in this analysis not doing that because K plus and K minus are roughly speaking not the same, right? They're independent. But in that case, I will have to keep track of their variations independently. Or alternatively, what you can do is that here you can re-express everything in terms of K plus and K minus and then expand this everything. But this expression is simpler, shorter. So if you can bring it.
In the action, you have expanded K to K plus and K minus.
Yeah, but I can here I can just simply replace this by K, right? Because it is anyway going to wedge product with something which is antisymmetric. And then here also I can replace by K because K acting on something else, several frequency. And similarly, you could have written a minus here. But you're writing in full K doesn't make any difference. And this I already told you is same as K is. Okay, is the variation clear? This one will only hit the K. This will hit both K here and here, but this is symmetric, so there's a twice. This is once again going to hit the K here, and there is once again going to be two variations, so the minus sign goes away and delta by K is there. So this I can collect and write it as first this. So I just collected this, and this together, and I use the fact that NQ plus NK is same as M of Q plus K because it's a linear map. And this last term is right now for the time being, nothing has been done with it. Now what I'm going to do is that I want this guy to be HG. Because you see it's almost coming to that form. The only thing that is stopping me from this becoming HG is that I'm missing a K plus here. Yeah. So if I make this HG, then I have to also subtract off the K plus, which I'm going to explicitly write in this form because here I wrote using K star K. So that's the thing that will help me. And now if we just expand this guy out. Or just this is precisely what you have here under the identification that if phi hat on shell is given by H. So this proves that equation of motion, all equations of motion derived from single action plus by hand constraint is exactly same as all equations of motions derived from sense action without needing any constraint whatsoever. So on the right hand side, it's just vanilla or Lagrange equation. On the left hand side, we do something by hand. So this is something that is giving you explicitly for the first time fully covariant action for type 2 supergravity, from which you can derive all the equations of motion. So in all the prior formulations, you would either have to sort of break the manifest Lorentz covariance, or you can use something like PST, in which it's easy to write down the bosonic sector, but then its supersymmetric completion is so complicated that, as far as I know, it has not been completely written down. It's possible in principle, but nobody knows it for sure. Okay. Any question on this one? If not, let's move on. Okay, now in this whole discussion, you would notice that I have never really constrained myself to only work with the bosonic sector. Like here, for example, I could have written down the full definition of K, right? And this whole thing would have still been true. So this thing, of course, we know is invariant under supersymmetry, right? The single action, it's the supersymmetry transformation that is given under the textbook. On this side, so far, I have not said anything about supersymmetry. But given the fact that they have the same gates invariances and they give rise to the same equations of motion, it's quite clear that this also has to have supersymmetry, right? You can't derive something supersymmetric from something which is completely non-supersymmetric without something going wrong, right? Symmetries of the action has to be narrated by the equation of motion. So now, this is something that you can explicitly say. So let me just make a couple of remarks about the supersymmetry transformations and Sen's formulation. So let me just mark this part. Essentially, the point is that you need to sort of figure out that how to assign. It's basically the same, technically same problem as the general coordinate transformation. We need to figure out that how to assign supersymmetry transformation properties to P and Q, such that two things will happen. One is that this extra field Hs, that will be a singlet, because just like under general coordinate transformation, it did not transform, under supersymmetry, it should also not transform. Because that's like an extra field. We don't want that to have anything to do with the symmetries in the physical sector. The simplest way to make sure that that doesn't talk to anything in the physical sector. And on the physical side, it should have the same supersymmetry transformation properties on shell for the HG or F5. F5, right? F5 has supersymmetry transformation properties, no. Right? How does it transform and what is it going to be? So HG should have the same things and all that. So and yeah, another thing is that we also need to tell you how to propose a supersymmetry transformation of this map M, because that's also a new ingredient in some sense. Okay. So the thing that is proposed, let's first work with the map M. So by M here, I really mean that the matrix M. Okay. This is exactly, I mean, something that you would compute from Susi. So A is something that I told you that once the physical metric is given to me, G, I can explicitly construct what this A is. So in some sense, this is some sort of function of the metric. So this is not going to be anything new. So if somebody gives you some, so suppose you have some sort of, function of G mu, supersymmetric transformation of this is precisely what you would expect by doing a supersymmetric transformation of the metric, and then just looking at how the function varies. So all we are saying is that you do the same thing for the m. There is no need to propose anything new or radically different. Think of it like something that you can explicitly figure out how it depends on the metric. You know how the metric transforms on the supersymmetry. Just honestly copy. And you will get some answer. It might look very complicated, but you will get some answer. Okay. So that's the first thing. Field, which is the fourth form, you propose that in supersymmetry transformation is precisely what you would ascribe for the number 4 potential in the superreaction formulation. Okay. And once you propose that, the supersymmetry transformation of the Q is kind of fixed by demanding that HS does not transform. Which is by taking the self-dual part of the supersymmetric transformation of the field state, DC form. Why? Because simply speaking, remember, we want to demand that supersymmetric transformation of HS is 0, and this is precisely something that relates. So demanding this is demanded. So if I postulate something for this guy, it automatically implies something for this. They are not independent, which is exactly the same thing that we have for general boundary transformation invariants.
Yeah, the gates to
Yeah, as well as the gates, right? So we want this sector to be completely insensitive to any of the physical symmetries, anything, it does not transform at all. That means that one of the things, if we tell you how to transform, then it automatically constrains the other one.
You want a minus there or a plus in front of the heat?
Sorry, this is, yeah. I wanted to this and I forgot. Yeah. That's why there is a minus sign here.
Yeah.
And finally, in principle, sense action also has this K, which is, as I'm repeatedly saying, that it's not really just a classical source because it has dynamics in S2 as well. So, but for that, this K is the same thing that appears in the same pseudo action. So it's exactly same as what it would happen to do for the K and the pseudo action. So you know how I have erased the K, but K has B2 wedge F3, for example. So you know how Raman field transforms on the SUC. You know how Raman field flux transforms on the SUC. You know how the fermions transform on the SUC. So given any of those, you know how K transforms on the SUC. And this is precisely what you would do for the sense action as well. And given these transformation properties, one can show that this 2B action that we wrote down in sense formulation is completely supersymmetric. This is a very long computation which doesn't necessarily give any insight, it's just a technical computation. Interestingly, you can actually prove this without doing the full technical computation. So once again, you see that there is a supersymmetric variation of S2 part which is going to match on both sides. So all you need to really sort of establish is that the supersymmetric variation of this S and the supersymmetric variation of this S1 that we were calling in the superreaction, those two agree. Because the S2 is same, so it's going to be the same on both sides. And you can sort of indirectly argue that depending on certain results that are already known in literature over course of many decades, in fact. This is what Ashoke does in his 2015 paper. But those arguments are also it's quite convoluted and involved. But then one can also do a simply just an explicit computation and establish this. But either way, the bottom line is that the supersymmetry is completely intact once you have this. What is more interesting is that, sorry, I'll just finish this ahead. What is more interesting is that you see that you really don't need to introduce any additional sort of super partners for the fact that there is a P and etc. Simply because this additional field, we just want to be completely similar in the supersymmetry. So it's something that's going to be completely decoupled. And then you really don't need to introduce any other additional formulas. So whatever formulas you add in this traditional pseudo-action description, they suffice to establish the full supersymmetry of the action. Which is good, because if you have introduced additional formulaic sector, then somehow you have to figure out that how they would get it, be decoupled, because you know what is the spectrum of supergravity. So you can't introduce additional fields without somehow doing this trick where they completely decouple. Yeah, it's both.
Oh, that's HS.
This is HS, yeah.
Oh, okay, I thought that's HD.
No, H, yeah,
HD should transform.
yeah, HD will transform.
Yeah.
Yeah. Just like in general coordinate transform, right? The Pilsner did transform. It is a form. But this guy, even though it has indices and everything, we don't want it. And I should also say that, okay, this is something we are today focusing only on type 2B supergravity, but of course, Sen's formulation is not particular to only type 2B supergravity. You can use it in any 4 and plus 2 dimensions. So for example, in 6D, several groups have written down several candidate Lagrangians for different purposes. Either you're trying to describe M5 wall volume actions or some other theories with 2, 0 or 1, 0 supersymmetry. There, of course, you have a different spectrum, right? And you may not necessarily have a pseudo-action description to match with. You're writing something completely new. In those cases as well, it's basically the same philosophy. You can basically figure out what the supersymmetry transformation property is, demanding that the total thing is invariant, demanding that this extra thing decouples. And then usually, and this M doesn't need any new supersymmetry transformation property. It's just an honest computation of, if it's a supergravity, then it's an honest computation. If it's a background metric, then of course this thing is insensitive to, if it's a global supersymmetry is insensitive to one. And then these two can be figured out by demanding that the total thing is invariant and by demanding this more or less up to trivial field redefinitions and such.
Also, like last time, remember, like P and Q, they have some weird, like transformation rules under decomorphism, right?
Right.
So basically, that's local translation, right?
Mm-hmm.
And to Susie,
Yeah,
is this consistent?
this is consistent. In fact, this is consistent even with a much larger thing, because this whole structure sort of inherits from the space-time action of that to be string theory. And there is a whole infinite hierarchy of gauge symmetry that is there. The local supersymmetry and general coordinate transformations are just two small subsectors of that infinite hierarchy. The whole infinite hierarchy has this, in fact, similar mathematical structure. And it's completely fixed by demanding that this extra thing doesn't transform, and then this action has to be invariant, and then typically there is enough data to more or less uniquely fix how these things will transform.
So if I can recap, so you summarize, so you're saying basically that because you're basically giving the you're using the same, because the same action and the observer action, they have very similar properties. In the same way that we proved that the equation of motion was the same, very similar arguments goes on and says that the supersymmetry of the observer action also naturally
Right.
Yeah, supersymmetry of Sen's action.
Right.
Because I thought I heard in the beginning when you started with the Susie here 20 minutes ago. It is, I mean, usually, the logic is usually you say you have an action and then you have equation to motion. You have a symmetry of the action that gives symmetry of the equation to motion, but not necessarily the other way around.
I agree.
Good, okay, because that word was saying the other way.
No, so definitely not. Sorry. I mean, like free equations of masses that will have GLN symmetry, like of n particles. Typically, that is the lowest symmetry in the action. Okay, so so this is about the classical equivalence of the tactical supergravity, and I hope that by now you're satisfied that this is a fully covariant description of tactical supergravity without needing to impose any by hand constraints and etc. So this is actually a good point to stop, but I'm just going to sort of indulge on this ongoing trend that I'm consistently going over the time limit by just presenting one small calculation, then I will stop for sure. Is that
I heard the word small.
There's another. That's why.
of course. I think I've done this for every switch of board now. It's a small calculation in the sense that you would actually not need to do the calculation, but do something smaller. But it's also interesting because it's probably the only quantum result in supergravity that you can think of as a consistency check. Okay. So, in the very first lecture, I told you about this result by Witten and Alvarez Baum. I think 1981 in the gravitational anomaly. Right? And effectively, the point was that they said that if you have a self-growth field strength on 10D, then it has a one loop gravitational anomaly as you would expect because this violates chirality, and anything that has a violation in chirality, if you couple it to gravity, then you typically get gravitational anomaly. And they say that the contribution to the gravitational anomaly is one loop exact and is computable by evaluating this hexagon diagram, where these are the gravitons, these solid lines, the internal lines, these are the propagator for the self-dual field strength, if I have. And the only problem they had is that they did not have any action from which they could derive the Feynman rules and do this computation. So what they did is that they said that let us propose a sensible which is a completely insane thing to do, but somehow it worked out. So what they proposed is that for the propagator, they essentially proposed that the propagator is something like being very careful about the signs and various minus i's and etc. etc. So they essentially suggested the propagator of two field strengths. So each of them has 5 indices. So it's basically a 2-point function of f mu1 to mu5, k f mu1 to mu5 minus. This is what this guy is. Right? This is what they suggested. And permutation is simply where now k mu1 would be mu2, and then g mu1, and etc. So one of the metric factors you replace by this take one at a time. So you have 5 terms essentially. And this is a propagator that you would expect of field strengths, not for potentials. Gauge potentials as a propagator which has no k factors in the numerator. Field strengths, because they are d of the gauge fields, they have an additional factors of k in the numerator. And so they suggested the first thing is that for use of propagator, they said that let's use the field strength as a propagator. That's the one thing. And the second thing is that you would need a vertices, like cubic vertices, with one graviton and 2 field strengths. So they use the fact that the graviton couples to the stress tensor, and the stress tensor is the one that you compute from the pseudo action, and then only look at its self-dual part. So essentially, what they're saying is that they have an action with the F edge star G. If this would give you that propagator, in some sense, if you think of like F as the sort of dynamical variable, but then they want to couple this H mu with T mu, and this is where it gets problematic because they don't want to use the stress tensor that you would normally derive from this. They want to use the stress tensor, which is derived from this, but then you further impose by hand F equals to star GF. So this is why they could not work with an action, because there is no way this is consistent. So this is the, and this is of course bilinear, right? They should have, just if you start from the F edge start, F kind of an action stress tensor, and then you evaluate its thing, it would have 2 factors of X. So this is what gives you the cubic vertices, right? And with this, they computed the anomaly. They computed this.
But this propagator doesn't care about self-duality.
This propagator does not care about the self-duality. This one does. And it's essentially the same thing, because you see that in each vertex, if it only forces the self-dual part of F to get emitted and absorbed, then it's effectively the same as if you replace this propagator by a projection of self-dual on both sides. So if you keep the propagator of self-dual things or not, it really doesn't matter as long as the vertices has this projector sitting in front of it. But for the propagators, what I would want to draw your attention to is that the propagator is that of the field strength directly, not the gauge potential, which is something like very strange to do in an 81, so to speak. And this was much before any of this story about the whole round sectors and anything were even uncovered. And this is a computation that you can do and you get some answer, right? You get some answer. And we know this answer is correct because this is the answer when you plug in to type-2p supergravity gravitational anomaly computation. This is precisely the thing that you need to make sure that the total type-2p supergravity gravitational anomaly vanishes. So this has 3 possible sources. One is from the self-dual field strength. The 2 other comes from the superpartner of the gravity now, which is some spin free half particle, and then you have spin half liberty. So if you take this one to be left-handed, you should take this one to be right-handed. So both of them chiral. For them, computing the gravitational anomaly is non-controversial. They have standard action. You can just do a plain simple calculation and you get the answer. For this other one, the self-dual Raman 5 formulas, for them it was a problem. We didn't have an action. So they proposed something, computed an answer, and the consistency check for that answer was that these 3 together ensures that the total gravitational anomaly vanishes. This is probably one of the less celebrated anomaly cancellation in string theory. Typically, the other ones where gauge anomaly and gravitational anomaly cancels are more exciting. But it's crucial for our case because it suggests that this prescription somehow is the correct prescription. Even though they could not derive it from an action, if someday somebody comes in front saying that I now have a candidate action, they should be able to reproduce this exact same computation. Okay. And of course, in general, if you do any loop computation in supergravity, it's not going to make sense because it's not a, at least as far as I know, it's not supposed to be a renormalizable theory. But this is a computation which makes sense because it's one loop exact. Okay. So this is once again repetition of whatever I said in the first lecture, but just to refresh your memory because it had been quite some time back. So now we have a candidate action, right? And now we want to make sure that this thing works out. So all we need to make sure is that show that sales action gives you the same final rules. Then you're done. If you have the same final rules, then your computation is already different. And you see already that this vertex factor is going to be the same. Because as I keep on saying, that you can generally prove that the stress tensor that you get from the pseudo action by imposing self-duality by hand is precisely what you would get from sense action if you just derive it without any constraint whatsoever. You just do a knowledge computation. So the graviton coupling to the stress tensor, which gives you the vertex, it's the same vertex that you get from sense action. And this thing is looking very promising because sense formulation by definition uses a field strength like variable. So the propagator that it would have should have something like this. Okay. And this is what I want to show you. 10 minutes. Okay. So, in fact, to evaluate the propagator, it's a little bit faster and simpler to just look into the d equals to 2 case first. Because the manipulation that you do for finding the propagator in d equals to 2 immediately generalizes to higher d, just have indices. So let's just quickly see that. So in d equals to 2, your action would look like this. So instead of p, you would have some scalar phi. And instead of q, you would have some one form which I'm calling a. A is with respect to p. And this is just, by the way, flat space time computation, right? Because this whole thing is like a flat space propagation, and then there is a minimal coupling to H to P. Now you can do a Fourier transform of this and rewrite this as an action in the momentum space. I'm using the same symbol for the Fourier transform. I hope it's fine, but I'm going to write the argument of the momentum explicitly. What do you want me to put at the okay. And then okay. Everybody agrees? I just took this inside the bracket with the overall half, so that's why that will be given 4. That's the only thing. Otherwise, it's just simple Fourier transform. Now comes my favorite step, where you define a new variable called phi hat, which is precisely this linear combination. What's good about this linear combination is that if you now evaluate these values, I had a square, I had minus a. You can just quickly convince yourself that, or maybe for benefit, just write the steps in once. I just expanded the product out. The only thing is that phi minus k would imply that this becomes plus because there is a k sitting here, and of course these are going to be minus k. So that's why one of the cross term is a minus sign and then one of the cross term is a plus sign. But here I can just simply change the level k to minus k. The measure doesn't get affected. And relabel the mu to nu, and then just identify that these two are essentially the same term. And then finally, and once you combine them, this term and this term, if you add this, so this becomes minus 4a. This is precisely what we have here.
Shouldn't it be to the fourth in the last one?
This one is 4 because we multiply 2 of this.
Oh, yeah, you're right.
I think the first one is a factor of 1 over k square extra. The first one, no? Like,
Sorry, yeah, this one doesn't have this. You're right. That's right. Okay, now this, if you just relabel k to minus a and mu to mu, you can say the matrices. This one becomes exactly the same. These two are essentially exactly what we have there. So this is L Sen as a function of momentum k. And then now you have this extra term, which is mu for mu squared minus k. Which means I can write L Sen this thing as phi hat a squared I have minus k, and then bring the other line this side, so we got minus n. Now, this is something that I promised some lectures back, that in position space it's very hard to see the decoupling between the physical and non-physical degree of freedom, but in the momentum space it would be very easy and straightforward, even at the level of action. And which is good because when you're doing Feynman rules, this is the thing that you start off with. Now, if you simply think of this as some degree of freedom phi hat, some scalar degree of freedom, then it does not talk about mu at all. So any scattering process, and of course, if you have an interaction, remember we had a rule that interactions should depend only on A. It cannot depend on phi. So if you have any interactions, then that's the part that will sit there. So in any scattering processes, if you have external phi hat links, then you can completely disregard this, and those will be just free propagators, free theory. Albeit with a negative definite kinetic term, so it's not going to be unitary. But this sector is going to be completely well defined, and if you have external legs A sitting there, then it's okay to completely forget about phis and just simply focus on whatever you get from it. And it also tells you that why this is something easy to do in momentum space and not so easy to do it in position space. Of course, it could have, but it could have looked very early. It's simply because look at the field definition we did. There's a 1 over k square sitting there, right? Which is a nice thing to do in momentum space, but not necessarily a good thing if you want to Fourier transform back into the position space. And now you realize that this is the kinetic piece that is there. And so the propagator is going to be essentially the inverse of this. But the inverse of, while computing inverse of this, we need to keep in mind that these guys are self-dual. So one way to make it more transparent is
We replace the H with F.
yeah, essentially, but just one more.
Well, you could implement self-duality by the like-term coordinates.
Yes, in fact, in chiral bosons, that's usually the simplest thing to do because you need to only worry about either A plus or A minus. Other thing is completely this, but you can do it in a bit more covalent way, which is a good thing because if you have more indices, then like one is not a natural thing anymore. Okay, so let's just focus on the kinetic now. We had NUK and with minus sign, right? So minus 4 NU is squared, meaning of minus K. So what we can do here is that we can write this thing as the same factor here, and write this guy as some where P plus mu is half equal to mu plus epsilon. In fact, I would also use the minuses. Okay, I just replaced something which is trivial because this guy is same as this guy and this guy is same. Yeah. Now I can alternatively write this as upstairs A and bring the projector just sort of figuratively something on the right and thinking of that this is acting on the left. But then now I need to change the sign of this to be minus down. Is this something obvious that if you lower, because if you lower, this guy is not going to get sensitive, but then this one is. Okay, so this P minus.
So maybe you should write that. So you say that maybe write the same formula with.
So yeah, so it's just E plus mu
No, that's the
theta mu rho theta mu rho prime is P minus rho prime.
Yes.
I'm using that.
and vice versa.
And of course, vice versa. You starting from this, you can derive all the other ones. And this one I'm not going to touch at all. It just stays whatever it is. But then now I can think of the propagator as the whole factor sitting in front, which is essentially P minus K and P plus, or maybe just symbolically write this thing as A dot equals 1 squared. And sorry, this one would have gone upstairs in this one. So the propagator, or this is not propagator, this is the kinetic term, so to speak, in the momentum space. The kinetic term is not just a factor of K's, but it's sandwiched between two projectors. And you see this is consistent because any kinetic term involving a self-dual thing should only take contribution from the anti-self-dual part. This kinetic term is just making it manifest. That is, there is a P plus sitting on this side, which makes sure that whatever enters here is self-dual. And there's a P minus sitting on the leftmost side, which makes sure that only the anti-self-dual piece contributes. And that's why this one has to be raised. So any kinetic term for cell-dual pieces would be a map from the cell-dual to the anti-cell-dual thing. So propagator should be in formal sense inverse of that. So when we want to invert this to find the propagator, because the definition of the propagator has not really changed. Also you have the kinetic term is basically the formal inverse of this. It's basically, so if you call this some sort of fancy K, what are the indices they use? Tau prime, this entire thing. The propagator delta, or something that it should have this property that delta tau prime fancy K tau prime identity. And the easiest way to do that is simply take this and switch the projectors. So delta tau prime, I'm claiming, oh, there was a -4 here, right? So that doesn't go anywhere. Unfortunately, that's the normalization you get. So you have a -1/4 here. Now you have P plus K. And is this here? Why this is the inverse? Look at it. The rightmost side of this is P minus. Leftmost side of this is P minus. So this P minus simply you can collapse. And then K tau becomes K squared. Then
Why can you collapse it? P minus times P minus is P minus. If it's a projector.
yeah, but I mean this P minus is essentially going to sort of be sandwiched between this A's, right? Then I can just do the same thing in reverse order and then just
Oh, not that P minus times P minus.
yeah. And then so those P minuses would sit there, P minus, and then this K would become K squared. I can always undo this operation, right? The same operation where I can have this.
I thought we were checking the delta K.
Yeah, we are checking this one.
Right, so then you don't have an A, you have a
No, but I mean, okay, you
K
can.
times P minus.
Yeah, but you should really think of this as some sort of inverting between this, right? This is the whole kinetic term that we are inverting.
But why has K actually?
Which K? This color K? Because it's contacting with one A and
Oh, okay. Oh, exactly.
it's some sort of
Yeah, it's not the. Yeah.
maybe K is not a good phrase, so let me call it some uppercase I. Now I think there is the one flaw.
Yeah. So
Yeah, sorry.
if I do that
Mhm.
combination, well, so you're gonna get a K times a P minus times a P minus times a K.
So this thing, then I can just always sort of shift it. This P minus times K, I can shift it and write it as P plus times A, which I can forget about it.
It has to be like a functional matrix. So type what you wrote there. There are no A's there, right? It's just a delta and an R.
But you should think of this really sort of being sandwiched between the A's, because that's what you are really after.
No.
But
I don't think so.
what's it as a big problem with, I don't want two external tau. So tau prime trying double prime, it's a delta.
Oh, okay, yeah, yeah.
Was it something like that?
Sorry, just say it again.
Don't you want on the, what is that, the left hand side on the equation above there? Yeah, with delta and I.
Okay, instead of contracting this, I could have had something else.
Yeah, when you contract, I guess you get a trace or something like that.
Yeah, and then eventually this is the thing that I want to evaluate. I mean, this is just I'm just being lazy here. I'm just skipping some of the steps in between.
Okay.
It's essentially what
it shouldn't be two dimensions, so.
the case will be true in any dimension. This is not a, yeah, it can have some factors and numerical factors and all these things. But yeah, and then I'm not interested in that. I mean, this numerical factor can be something else. I'm just worried about the structure.
Yeah.
Right. The structure is simply, it's simply saying that if you have this structure, finding its formal inverse is something you just replace the order of this P plus and P minus. That's
So-
okay.
The way I think of it, or the way I can make sense of it, not by adding some a's or thinking about that, but you know, the piece takes this vector and makes it either into a k minus or k plus, take concordance.
Yeah,
And k squared is k minus times k plus.
exactly.
So when you're taking the things in the middle, you have one k minus, one k plus, and it cancels the k squared.
Yeah,
So, okay, that I can see.
that's the essential explicit way of saying it in 2D. But I'm just saying that this is something that coherently goes through as well if you just have more indices. Yeah. Yeah.
And another small thing is, I guess, because the T prime is on the left side and T, then I guess you want to switch the horizontal position of tau and tau prime on the left hand side of your delta.
Yes, you're right.
And counter as well.
Yeah. Yeah, that's the correct. Positioning of things.
But you know, for higher order, I'm not so sure because it's really, it's like a projection operator. It doesn't go very.
No, it doesn't need to go away. It can stay there, right? It's perfectly fine. I mean,
Yeah,
if
but
you're-
you want to cancel the k squared, so is it really canceling?
it would, because this P minus is something which is a very harmless transformation of what is doing into the case. So there would be one combination which would give you k square, and then there would be another combination which would give you the antisymmetric part of the case.
How does it even look like in high dimension? Then, how does this projector look like in 6 dimension?
Yeah, this will
Not in
be
2 dimension.
half one plus star essentially.
Right.
But this
Right, so how
one, this
does it-
one is now the identity map of the forms. So it
Oh,
will be
no,
product of
but
index.
But then you have, it's not k, but it's this k times.
Yes. It won't just be k. I mean, this is, let me just finish the 2D story and then I'm going to write down the expression. Of course, you have the other things which are carrying indices.
Yeah.
But the only thing that you need to focus on is that if you have something that is sandwiched between these two projectors, this function of the case, like there is a f of k that is sitting there, you really don't need to have a different f of k. The structure is such. This is not going to be true for any f of k, but this structure is such that k nu by k square is such that if you write a new thing with the projection order switch, it's going to give you essentially the formal inverse. Okay. If this is not something that you like, you can just simply start from here and just use path integral, find the propagate, right? Just use the 2-point function computation, simple and straightforward as that, and you will land up with the same answer. It's not going to give you anything different.
Yeah.
I'm just sort of,
I believe you, I don't see it, but no, I believe you. Point.
yeah, I mean,
But I don't see it.
this is something that you cannot immediately see it maybe, but it's something that you can explicitly check.
So can I separate, if I take k squared, can I separate that into a p plus piece and a p minus piece, writing k,
Yeah,
p plus, k plus, k, p minus. So. Something which is not very local, so. Sorry.
no, it's, yeah, I mean, K is K is something like, so if you have K, then you can write it as K as P plus K plus P minus K.
Right. Now take square this.
Yeah, you can square this and you will get all sorts of terms, but like what exactly are you after?
So what I'm after is that you take now one of these terms, which is going to be k, p plus k,
Yeah,
and you're replacing it with k squared.
yeah.
When
But
you multiply
this
these
is
things.
this is perhaps not the wisest thing to do. Like, don't change the denominator. Instead, what I'm saying is that in numerator,
Yeah.
you get some contractions of k. You realize that okay, this is only going to be some sort of contractions of the k's, right? So the only contraction that you can form is basically going to be k squared. All the other contractions that will come because of the epsilon tensors are going to be identically zero because k is going to be symmetric and epsilon is antisymmetric. So that's the only contraction that will survive.
Oh, I see something.
So you might disagree with the numerical fact, and you might say that okay, this is not k square as Klaus was pointing out, that it might be 2 of times k square, or in dimensions it might be 10 times k square, stuff like that. That might be possible. I'm not being very super careful about the numerical fact.
No, okay, no, but then you said the good thing. So I take k, p minus k, multiply it together, I get k, p minus k. But if I have the same k on both sides, epsilon.
Exactly.
So then,
Exactly.
then
Exactly. That's what I'm saying.
good.
Yeah. So that's why I say that it is only true for this kind of thing. If you had like 1k, for example, if you had just for some reason 1k and then some say one other random vectors, it might not necessarily hold. It's this particular thing which has this property. The finding its formal inverse is very easy. You just switch the order of these propagators. And then what it means is that okay, the actually the propagator is something that would be I times this delta. So and this it would be up to some numerical factors. Essentially, it's sandwiched between p plus and p minus, but it's essentially k mu yes. And which is precisely the propagator that they found or they proposed. Now, how do you just generalize this in higher dimensions?
Well, it's not that propagator. Right? That propagator is missing the projection.
Yes, but as I said that
They put them in the.
yeah, it said that I mean because the vertex has the projection.
Yeah.
The actual computation is insensitive whether this propagator has this or not.
Yeah.
But of course, if you have it, it's kind of like not doing anything. Okay, so now how do I uplift this to b equals to 10? It's not just adding more indices. There is only one layer of subtlety that comes in higher dimensions, which is not there in b equals to 2, which has to do with the fact that in b equals to 2, this extra field phi is a scalar. So it really doesn't have any gauge symmetry. It has a shift symmetry. But in higher dimensions, this phi is going to be replaced by a form dp, which has a gauge symmetry. Which means that to find the propagator, at least that gauge symmetry, we need to gauge fix. So this is the uninteresting gauge symmetry that I was talking about, that you can change delta p by some p of lambda 1, and dp doesn't change. So this whole action is gauging variant under this.
Or isn't this a price you pay also using field strengths instead of?
Of course. Yeah, because I have working with field strengths, it means that the gauge transformation has somehow shifted to something else. Right. So this gauge fixing is, of course, you can gauge fix however you like, but one of the gauge fixing terms, which is quite natural, is this one. This is essentially in components like del mu, p mu, whole square. It's kind of analog of the Lorentz gauge in Maxwell, for example. Okay, and it's a natural sort of gauge choice given that you are doing everything in a Lorentz covariant fashion. So just pick, and it's a U1 gauging variant. So just pick the simplest Lorentz covariant gauge choice that you have, and this is it. And then essentially, just like we define phi hat, we need to define P hat, but now of course it has 4 indices, P, mu, rho, sigma, say, A. And this would be P, mu, rho, sigma, K, minus xi, Q, and then another index of tau, mu, sigma, K, tau, K squared. So it's essentially the same shift you did, except that now you have more indices. And with this, once again, you find exactly this sort of decoupling. And the propagator essentially is like what you would write down there, up to some numerical, overall numerical factors, which is immaterial because you might not be working with the same normalization in both formulation. And then, as I said, that once you have the same propagator, and I've already argued that you have the same vertices, then you produce the same computation because it's the same Feynman rules. The only difference is that now this Feynman rules is something that we derive because we have an action. We could just simply straightforwardly do a computation and derive. Okay, so this is a natural stopping point, but I just want to emphasize one thing that we start off with a very unusual action, having additional degree of freedom, which has somehow decoupled. And then you have some sort of complicated structure. But then the whole thing is that either through Hamiltonian analysis or through this momentum space analysis, it's very easy to see this decoupling. And then just simply focus on the physical sector. And then you do computation exactly as you would do for any QFT in any background. You just find the Feynman rules, you just do the computations and so on and so forth. So at some point, if we continue, I can talk about one explicit, a different quantum computation that you can do, but for the chiral boson sector, which to my knowledge is the only explicit perturbative quantum computation that is done in this formalism, except for this one, which is a, in some sense, consistency check. Okay, so there are some applications in chiral bosons that we can discuss, and then there are some applications in type 2 supergravity that we can still discuss, but it is really up to you. But okay, this is, I think, a good stopping point.
One question,
Yes.
like, well, let's say we look at introduction of energy and the sets architecture. How do I take introduction from there? Are they saying, I mean, for the motion, if I don't care about the motion, of course, like, it should be the same, but at the actual level, is there something motion you're going to?
Yes. So, okay, first thing is that you should really think of pseudo action as not the best starting point for doing a KK deduction, because it's really not the action for technical. It's an action for something much more. So in sense action, now you can say that, okay, if you really have a consistent action, then I can do a KK reduction or any reduction that you want, and then you should get something sensible out of it. So these are the two applications that I have in mind. In fact, these are the two papers of mine that we wrote. One is that you can do a circle compactification of type 2b and show that it's actually T-equal to type 2a.
Yeah.
And how do you go and see that? And another thing is that you can also think of this type 2b on ADS 5 times S5 and make an interesting connection with some prediction from ADS CFT, which was somewhat missing in the literature. So
there's no explicit dimensional reduction to be done yet, or
you can, if we have, right? If you do a circle reduction on S1, you have to do an explicit dimensional reduction. But I can discuss that next time.
okay. So I mean, like there are already papers like that people did that, right? This one. Oh, we did it.
Yeah.
Okay.
For type 2b, we did it, but for even before that, in 2019, Ashok's paper, he talked about circle reduction of chiral bosons and for 6D theory, the reduction on torus. And then Neil Lambert's paper, they discussed 6D theory reduction on torus, on K3, and on any arbitrary Riemann surfaces even, if I remember correctly. And these are interesting for other reasons because these have some interesting connections with like cyber-Witten type gauge theories and etc. etc. But yeah, there are several compactification reductions that are known, and in some sense, conceptually, nothing new happens. You have an action, you just do an honest compactification. You put your answers, you use the fact that something is depending on the circle directions or the extra compact directions in ways, and then you use the answers to plug it in your original action, get an effective action, and then it's up to you whether you want to look into all the modes or whether you want to. Of course, but then there are some small subtleties that happen. But if you are worried about the fact that whether this extra field can kind of get mixed with the physical field through this dimensional reduction and everything, that is where this decoupling comes into the play. The fact that we have shown that this decoupling is exact at the quantum level, it means that no matter what you do to this action, this decoupling is going to remain exact in the lower levels. So a good rule of thumb that all of these analysis, including ours, shows is that you just do reduction and just focus on the physical sector. Just don't care about what you get from the other additional sector in the reduction pieces at all.
So after all, just there are some slightly subtleties, but overall there's nothing.
No, conceptually it's not a very new or non-trivial step. The two subtleties comes from the fact that you dimensionally reduce the field strength directly, because otherwise you do an ansatz for the potential and then that dictates how the field strength is getting reduced. Here you have to do it at the level of field strength directly without thinking of it as a field strength. And the second thing is that the gravitational coupling enters through M. Right? So the M you need to figure out how to reduce. So these are the only two new things, so to speak. The rest of it.
Also the symmetries are sort of fine.
Yeah.
Like I guess the P and Q, the demorphism part is like.
Yeah, P and P, because P and Q are not.
So after reduction they just behave normally as the ordinary tensors in 9 dimension, for example, or.
No, so so
you can do some redefinition together.
Yeah, you have to do something to bring them into the standard form. Of course, the extra piece is going to be there, and you don't care about that. But the physical piece, because for example, in circle reduction in type 2b, you know that this has to be T-dual to the type 2a, and that has a very standard formulation in terms of potential. So that was our point of interest, that how does this, which is field strength based, become something which is potential based after a circle reduction. And so the answer is just doing several field redefinitions appropriately.
Thank you.
Yeah.
Also, another question.
Yeah, go on.
If I go to 4D
Mm-hmm.
and I use, let's say, curvature to form, I can form some, let's say I'm Euclidean for simplicity or whatever. There is possibility of having self-dual gravitational, like curvature to form.
Yeah.
So can I do some self-dual, like gravity?
Wait, you have this is only in Lorentzian, right? You're telling me.
Yeah, but I think he wants to be Euclidean in 4D, which is fine.
Yeah.
If it's
whatever,
Euclidean,
whatever signature does it's too much.
Yeah. This is an interesting question. In principle, I would
So
say,
4D we have gravitational instant solutions, right? Like
yeah, of course, because it has to be Euclidean. Yeah, in principle, you should be able to use this to find some description of that, but I don't think anyone has done that. But I don't see any.
It could be useless at all, but I just asked.
No, but yeah, I mean, I don't think it's useless. I mean, I think it's an interesting question, but for sure, this is something that one can look at.
Okay. Because seems well, this formulation is like you have a flat case and then you couple to gravity, but if you start the gravity sort of to begin with, it's.
But then you see that what is self-dual, that field strength itself is sort of kind of defined independently, right? So somehow.
I mean, we're using field by so.
Yeah, somehow I think that should work.
Okay.
Yeah, it should not be a problem. But another thing is that I also want to emphasize is that as we were discussing that this also presents a quite broadening of the paradigm of what we mean by action principle, right? So it is possible, this is a possibility that, for example, Ashok mentions in one of his papers, 15 or 19, I forgot, is that maybe you can use this philosophy, not necessarily the fact that it's self-dual, but this philosophy to target other things in physics which are supposed to be something interesting, but you can't describe in terms of an action as of yet. Like one example, clear example is, for example, the Vasilev high spin equations of motion. So this is, in my mind, this is a very interesting thing to look at. I mean, one doesn't know whether how far you can take this approach and etc. But it's an exciting possibility. And it's also something that is supposed to sit very nicely within string theory. Of course, I mean, it's all conjecture, but one would expect that there is some sort of, some phase of string theory in which you have high spin gravity. So, yeah, I mean, okay, there is definitely some technical aspects which are very particular to Lorentzian 4n+2 dimensions, but then there are some conceptual aspects which is definitely in my mind something that has much broader scope than just 4n+2 Lorentzian manifolds.